Hello everyone. Thank you for coming to this talk. I'm Yu from UC Irvine. Today I will talk about how to create SVBRDF maps using Generative Adversarial Network. Real-world environments are full of objects with different types of materials. How to capturing spatially varying reflectance of those materials remains an important and challenging research task. Traditionally, to avoid the manual process, people use customized hardware systems to densely sample illumination and viewing directions, followed by post-processing such as fitting parametric BRDF. This leads to precise results, but requires complex, calibrated, and expensive hardware. Recent work has explored lightweight capture setups, such as smartphone captures with flash. These methods generate plausible results in less constrained environments. However, with one or few captured images, they cannot achieve high-quality results. A widely used material model in the industry is Cook torrents. It allows representing many opaque surfaces with just 4 parameter maps: the surface orientation, the diffuse and specular light reflection, and the shyness or the roughness. Together, it is SVBRDF. We want to reconstruct SVBRDF maps from several smartphone captured photos accurately. Using a small number of inputs to estimate a large number of unknown is a fundamentally under-constrained problem. There usually exist many material estimates capable of producing renderings that match the measurements. But many of these estimates can be unrealistic and may not generalize to novel illumination and viewing conditions. Previous papers provide many kinds of priors to this problem. With the help of the prior, it can reduce the solution space and reconstruct plausible results. However, most of the priors are not robust. Some of them are lack of global constraints on individual maps, and others produces unexpected correlated maps and to interpret dark pixels as shiny. We're looking for a good prior, which could make SVBRDF maps look more natural. The Generative Adversarial Network may be a good solution, since it can generate new photographs that look at least superficially authentic to human observers. GANs has become extremely successful in the past few years in various domains, including images, videos, 3D shapes, and etc. StyleGAN is the most recent work for generating high-quality realistic images, mostly of human faces. We will build our work based on StyleGAN too. While StyleGAN focuses on projecting portrait images into face-specific models, their analysis can be adapted to our problem. Based on StyleGAN 2, we train our MaterialGAN to generate plausible materials. MaterialGAN learns global correlations in material parameters, both spatially as well as cross parameters. Sampling from the MaterialGAN latent space produces plausible, realistic materials with complex variations and diverse appearance. Here we show a video of generated material from moving in latent space linearly. It's producing plausible nonlinear morphing results. The maps for each SVBRDF are stacked in 9 channels: 3 for albedo, 2 for normals, 1 for roughness, and 3 for specular albedo. We account for this by adapting the MaterialGAN architecture to have 9-channel outputs. MaterialGAN is trained in TensorFlow with the same loss function and similar hyperparameters from StyleGAN 2. All the training data are from the previous paper with a resolution of 256 by 256. We use MaterialGAN as a material prior for SVBRDF acquisition via an inverse rendering framework. To do the optimization, we're using a combination of a standard per pixel L2 loss and a perceptual loss that has been shown to produce sharper results in image synthesis tasks. A paper from last year has a similar architecture, but with the autoencoder as a material prior. Most of our comparisons are with theirs. Different from traditional GAN generator, MaterialGAN first maps the input latent space Z to an intermediate latent space W+. Comparing to style transfer, it computes a spatially invariant style from W+ instead of an example image. After injecting noise N into every layer of the style blocks to generate stochastic variations, we got the output SVBRDF maps. Instead of optimizing Z, we optimize W+ and N in a particular manner. Please refer to our paper for more discussion on this. Now, let's look at some results. We implemented our optimization framework in PyTorch and tested on around 40 synthetic data and 40 real captures. For all the results, please check our supplemental materials. We show a video for the optimization process for better visualization, which is initialized from constant maps. From the next slide, I will show some results for real capture materials with different types. We show reference images on the top, including both inputs and novel views, reconstructed SVBRDF maps on the side, and the renderings using estimated maps are shown at the bottom. A gift card rendered under environment light. Wood floor from the living room. Leather with small cells. Tiles in the bathroom. Specular book cover. Now let's look at some comparisons with Zhao from last year. In this example, I'm going to show optimization results by using different initializations. Starting from a relatively good initialization, both of our methods work. If we start from a simple texture map, ours is already good enough to converge to a clean and detailed solution. But it is not the case for Zhao's method. With the regularization of MaterialGAN, our method is robust to the initialization of the latent vector. How about post-refinement? Zhao's method is more dependent on the post-refinement via per pixel optimization. Without it, their method usually produces significantly blurry maps. On the contrary, Our results are already quite sharp after using our MaterialGAN-based optimization. Here we reconstruct SVBRDF maps from 7 inputs and compare the resulting maps and images rendered under 2 novel views. Since we are all doing optimization, both of our re-renderings can match input images. However, Zhao's method brings artifacts in the novel view renderings, since it is lack of global regularization on the maps. For a more challenging case, our method can preserve both global consistency and the local details, which makes SVBRDF maps more natural and useful. While our framework improves upon the state of the art, there are also some limitations. Our current BRDF model is shared by previous work, but certain common effects like layering on book covers, subsurface fiber scattering in wood, and isotropy in fabrics are not correctly captured. Our generative model and rendering operator could be extended, but the key challenge is finding high-quality training data for different materials. It will produce blurring or ghosting for materials with strong self-shadowing or interreflections. Solving for height instead of normal with a more advanced rendering operator may be able to predict shadowing effects from a strong height variation correctly. Also, our optimization is based on known illumination, where we need to have appropriate calibration at the beginning. To summarize, we propose a novel method for acquiring SVBRDFs from a small number of input images. We use an optimization framework that leverages the robust material prior based on a generative network, MaterialGAN, trained to synthesize plausible SVBRDFs. It produces high-quality SVBRDFs that accurately reconstruct the input images without relying on any good initialization. As a result, our reconstructions generalize better to novel views and lighting than previous state-of-the-art methods. We are grateful to the anonymous reviewers for their helpful suggestions, and we also thank TJ from Adobe Research for the hardware setup. For more details of this work, please move to our webpage. Thank you for your attention.